I mean, you know what? There are these sort of trilingual text that we are trying to read. And I mean, there is a function theory, as I was saying. You see, there is a function theory and the various properties of the data function. So there are the zeros. There is a functional equation. There are the explicit formulas. Okay. And there is the Riemann hypothesis. So I mean, on this left-hand side, what we have is algebraic geometry over finite fields, so over FQ, let's say. Now the zeros have a natural interpretation as eigenvalues of the Frobenius acting on the one-dimensional étale cohomology of the curve with L-adic coefficients. The functional equation is just Poincaré duality. And the explicit formula are the Lefschetz formula. Okay. While the Riemann hypothesis, let us say the Riemann-Roch theorem on the cross, the square of the curve, plus vanishing. Okay, so now on, so I mean, as I said, you know, this is not three things. I mean, they have relations 2 by 2, of course. I mean, there is no larger distance between these two here. So I mean, this one is the framework of non-commutative geometry. And the space that we have is the space X of Adel classes. Okay, and the replacement of Frobenius acting on this one-dimensional cohomology is the action of the Adel class group. But I mean, you can, of course, only look at the R plus star part, if you want, on the Hilbert space that we defined last time, which is L2 delta of X. Okay, and as we saw, I mean, this Hilbert space was such that, in fact, if we take L2 delta of CK minus L2 delta of X, okay, and it is the same minus sign as later, we get the realization of the zero. So the functional equation, we shall see what it is, but it's quite simple. It's just the fact that this map E, which I have defined, satisfies that E of F hat of X is just equal to E of F of X inverse. Okay, I mean, this is not yet a geometric interpretation, but it's the beginning. And now I'm going to talk about the explicit formulas. And now we shall see the explicit formula will be again a Lefschetz formula. Okay, but I mean, it will be a Lefschetz formula of another kind. Somehow it will be, and that's why I want to sort of start completely anew on this blackboard. I mean, it will be a Lefschetz formula of another kind in the sense that in order to understand it, we shall have to first understand rather rigorously and pedantically, unfortunately, but I will do that. We shall have to understand, if you want, the proof. Yes?
Just the last word in algebraic.
Vanishing. So we shall have to understand in a rather pedantic way, if you want, the approach by Attia and Bott, and also by Guillemin and Sternberg, of the Lefschetz fixed point theorem. And so, I mean, I will start by, you know, doing an explanation of the standard Lefschetz formula by using notations that physicists use, okay? But of course, I mean, this is not what we want. And then I shall criticize what I am doing, okay? Because else it will be a proof, if you want. And then we shall do it more pedantically, and we shall see exactly how things work. Okay, so that's the plan for today. Now, so let me first discuss the Lefschetz formula. Oh, sorry. Yes. Okay. So let me explain this in some detail. So, I mean, let's first start with the standard Lefschetz formula, if you want. So you start with a manifold M, let us say, and you start with the self-transformation, a diffeomorphism phi. So phi which belongs to D of M. And, okay, you begin by looking at the way this diffeomorphism phi, let us say, is acting on function. So if you have a function f, you can define an operator which is such that u of f evaluated at x is just f composed with phi of x. Okay? And I mean, of course, this would continue to make sense, this transformation, if instead of dealing with functions, we were dealing with differential forms. Okay? Because when you deal with differential forms, then you would just apply the map phi star to the differential form. Okay? Then you evaluate, you really compose the differential form with the smooth map. Okay? So, but I will first discuss functions, because, I mean, the generalization to forms is sort of obvious. Okay, and so what you want to do at first, if you want, is to write down what is a trace of the operator u. Okay, and of course the trace has to be taken with quotes, because this operator is not trace class. Okay, I mean, at the best, it's a unitary operator. There is no unitary operator which is trace class, of course. However, you see, what you want to do is you want to define the trace of an operator. I mean, if the operator was given by a formula of the following type. So if it was an operator of the form T of f, evaluated at x, is given by integral of a kernel, k of x and y, f of y, dy, then you know very well that under good circumstances, this operator is of trace class, and that its trace, so the ordinary trace this time of the operator T, is just given by the integral of the diagonal values k of x dx of the kernel. Okay? And I mean, this is, of course, a very naive and simple generalization of the trace of a matrix to be given by the sum of the diagonal entries. All right? So now it turns out that when you look at this operator u, I mean, you can write the operator u in the form of a kernel. Okay? And this kernel is just a Schwarz kernel corresponding to u. And in fact, you see, you can write u of f of x as being the integral of the delta function, delta of y minus phi of x, okay, f of y dy. So notice that this doesn't make much sense because phi of x and y are points of a manifold and you cannot take their difference, okay? So this is the first slopey thing that I am doing, okay? The second slopey thing that I am doing is that I am composing, which physicists do all the time, I am composing a delta distribution with a function, and that, you see, I mean, if the function, for instance, was taking, if I look at delta of phi of x, for instance, if the function is phi of x equals 0 for all values of x, I mean, this doesn't make any sense because it's always equal to plus infinity, okay? So, I mean, as we shall see later what are the conditions that this makes sense. But authorize me to just go on, okay? And then, so you write this formula, and then it follows, if you want, that you can apply this thing here, and that you have that trace, but extended, of the operator u is just the integral of the diagonal values, so delta of x minus phi of x, if you want, of times dx. Okay? So in other words, the trace of the operator u should be given by this. Now what is this? Is it easy to compute? It's very easy to compute because the delta function is 0 when phi of x is different from x. Okay? So I mean, it will localize around the fixed points. Now, around each fixed point, you will be able to take local coordinates so that this makes sense. So it will be given by the sum over the points so that phi of x is equal to x. Okay, so if you want the intersection of the graph of the transformation with the diagonal, okay, so such points x here, and then what do you have to do? Then at each of these fixed points, you have to integrate around the fixed point integral of delta of, let me call this x0 if you want, around x0 you have to integrate integral of delta of x minus phi of x dx. Okay? So how do you do that? Well, you take local coordinates around x0 and you linearize phi in the neighborhood of x0 so that in fact what you are doing is you can make a change of variables by taking the Jacobian at x0 of the transformation, okay, and applying it to a variable, let's call it epsilon or whatever, and then you have to integrate 1 minus phi prime of x0 epsilon, delta of that, times d epsilon. I mean, this is clear that it is what you have, okay? But on the other hand now, you can make a change of variables by inverting 1 minus phi prime of x0, provided the transversality is fulfilled. namely provided this transformation, this Jacobian, has not the eigenvalue 1. Okay, in that case, you can change variables. And of course, what you will get is, when you change variable, if I put 1 minus phi prime of x0 applied to epsilon, if I call that eta, okay, I mean, you will have the Jacobian of this transformation, but it will come in denominator. So it is clear that, in fact, what you have is the sum of 1 over 1 minus phi prime of x0 over all fixed points. And when I put the absolute value, I mean the Jacobian of the transformation, the absolute value of the Jacobian of the transformation. Okay? So this is what you get. But of course, I was extremely sloppy, as I said, okay, in doing this proof, under quotes. And I mean, but immediately you can see the power of this, because you see, if I were dealing with differential forms and not with functions, what would have been the difference? Well, the difference would have been that I wouldn't have scalar valued entities when I was dealing with this operation, but I would have a fiber, and if I were dealing with K forms, this fiber would just be the K's external power of the cotangent space at the fixed point. Okay? So that, in other words, when you are dealing with differential forms, instead of having a 1 here, what you will get is the action of the Jacobian in the K's tensor power. Okay? And the trace of it, because you are looking at something additive at this point. So in other words, what you see immediately when you do that is that if now you consider not functions, but if you consider forms, okay, and if you consider the alternate sum of the traces, sigma of minus 1 to the j, times the trace of the action of f, so let me call this f star if you want, but acting on the K's exterior, well, sorry, this is K's external power of the cotangent space. Okay, which is the same, of course, as dealing with forms. Okay, so what you will get then is that this is equal to an alternate sum, of course, on the other side, and but it's also sum over fixed points, so it's sum over fixed points. Okay, and then what you have is, in each of them, you have an alternate sum. Okay, but that alternate sum is just the sum of minus 1 to the k times the trace of the K's external power of the Jacobian phi prime at x0. Okay? And divided by the absolute value of 1 minus phi prime of x0, where of course this is equal to the determinant, the absolute value of the determinant. Okay? But what you have upstairs is not the absolute value of the determinant, but the determinant itself. Okay? I mean, you recognize a formula which computes the determinant as a trace on the exterior algebra. So what you have is a number which is just the sign of the Jacobian of 1 minus phi prime of x0. Okay? So of course you recognize a formula that, because now you can say that this alternate combination of traces, which was formal at the level of the action on these infinite dimensional vector spaces, becomes in fact not formal when you take cohomology. Okay? Namely when you, because the cohomology is finite dimensional, then you get immediately in a very, okay, I mean, André-Gauss manner, but you get the formula that sigma over the fixed point, so now I exchange the two sides. So sigma over phi of x0 equals x0 of plus or minus 1, where this plus or minus 1 is simply the sign, okay, of the determinant of 1 minus phi prime at x0. And I assume that all these points are transverse. So this sum of signs is simply equal to the alternate sum of the traces of phi star acting on the corresponding cohomology group, HK, of the manifold. Okay? So there were a number of things which were formal, okay, but I did it on purpose. Yes?
What did you denote by F star?
F star is the action of the pullback on differential forms.
Right.
Okay?
It's not a good notation because F is what a function. Yeah.
Well, okay, I mean, you can, in your mind, replace all the F's which were here by phi's, or, okay, indeed. You're right, Riku. This is phi star.
Right.
I'm sorry. Yes, this is phi star. No, that was a real mistake. Okay. I mean, what was a mistake was to use perhaps F for functions, but I don't know. That's not a bad mistake. Okay. All right. So I mean, we have this formula, and now what we want is to try to tidy up this messy proof that I gave. Okay, and make it as nice as possible, so that when we want to handle much more complicated computations, you see, I mean, this proof is fine when you deal with a single transformation. There is not much of a problem. I mean, you can go. But now we are going to deal with flows or with more complicated group actions. And then it is clear that if you stick to these notations where you have a minus and so on, you will be in a mess very shortly. Okay? So we do have to make a little bit of effort at the conceptual level and understand really what we are handling, what we are dealing with, and so on. Okay? And as I said, I mean, this is still formal in the sense that this is still a distribution trace which is defined at a formal level. What will be the hardest work will be to make this rigorous and to really transform it into a true trace, which is defined by cutoff and so on. In particular, you can see that there is a big difficulty when the transversality condition is not fulfilled. Okay? Because in that case, what you get are infinities normally. And you have to be extremely careful about this. Okay, so that's the plan. All right, so first of all, what I will do, I use the notation here, somewhere here, perhaps for the first time here. And instead of writing the determinant of a transformation, I wrote the absolute value of the transformation. Okay? So let me be ultra pedantic and define a functor. Okay? And this will be quite useful. So I will define a functor on vector spaces over R from vector spaces. In fact, it could be vector spaces over any local field. Okay? To one-dimensional vector spaces over R of C. Okay. And I mean, even if I were dealing with a local field here, I would always land in something over R of C. Okay, even though I would start with a local field, which can be periodic numbers and so on. Right.
What's the definition of delta?
Oh, delta is a Dirac distribution. Okay? So, I mean, at this level, of course, I will now give you an extremely pedantic definition of a delta. But at this level, the Dirac distribution is a function which is zero everywhere, except at the origin, where it is infinite, so that it has integral 1. Okay? I mean, that's the definition of Dirac.
Yeah.
And keep it in mind. I mean, that's a very good definition. Okay? It's a function. All right? Okay? So, I mean, you should keep it in mind. Now I will give you an atrociously pedantic definition, very shortly, of what is a delta distribution. Okay? But, I mean, intuitively, you should only keep that in mind. Okay, so, I mean, this functor I will denote by absolute value. And you see, if I have a vector space E, okay, an element, so I will assign to it the absolute value of E. And an element of the absolute value of E, so this will be a one-dimensional vector space, it will have the following form. It will be lambda times psi1 wedge psi n, absolute value, where the lambda is in R or C, okay, and the psi j's belong to the vector space E. The wedge is the ordinary external product. The n is the dimension of the vector space E. And now I have to tell you what happens. You see, if I replace, for instance, psi1 by eta 1 wedge up to eta n. So I know that this nth wedge product is, of course, one-dimensional. Okay? And so I know that this is equal to some constant C times psi1 wedge psi n. Okay, now the absolute value, then, namely if I take absolute value on both sides, okay, this will simply be equal to absolute value of C times psi1 wedge psi n. All right. And if you take a local field, this makes sense, because the absolute value of an element in the local field does make sense. Okay? So, I mean, this is sort of reasonable. It's a one-dimensional space, and so everything goes through. Now, so this is what I will denote by absolute of E.
Can you obtain it out of top exterior power?
It is. That's what it is, but I want the absolute value. It's not the top exterior power.
What does this say?
Okay, this absolute value is precisely, you see that, let me explain this. You see, if you have a manifold, let me explain you why I'm doing it, okay? If you take a manifold M, okay, and if you take a differential form omega of top degree, so that is a section of the top external power of the cotangent space, okay, of the manifold. But unless you have an orientation, you cannot integrate that. Okay? Unless you have a fundamental cycle, namely an orientation of the manifold, you cannot integrate that. However, you can always integrate over M the absolute value of a differential form. Okay? Because the absolute value of a differential form is a measure. And that is independent of whether the manifold is orientable or not. You can always integrate that. Okay?
So
Yeah, sure.
over R is just square of
No, over R, for instance, if you take over R, you see it's dt absolute value. Okay? It's not, okay, so I mean, it's a little bit pedantic, but you should keep it in mind. So, for instance, so I hope you understand this definition of this one-dimensional vector space, which is just the absolute value. I mean, you could, if you want it to be even more heavier notations, you could denote it by wedge n absolute value, okay, of the vector space that you take. But I prefer to denote it simply by E. Okay? So now this is a covariant functor. This is a covariant functor because if you have a map, a linear map E to F denoted by T, okay, then of course what do you know? You know that you have a corresponding map from the top external power of E. These are same dimension, which is the wedge n of T, okay, which maps to wedge n of F. Okay, and now you can take the absolute value of this. And this will give you the absolute value of the determinant. In other words, what I am saying here, okay, is that if I have a map, I will simply apply it to psi1 up to psi n, okay, and I will get this. And this, of course, when I compute it, it will give me the absolute value of the determinant of T, okay, applied to the various elements here. Okay, so you see, it's just a notation, but in practice, it's extremely useful, and okay, when one deals with more complicated stuff, it's important to keep it in mind. Now, what one calls a density, so a density, a one density, or a density if you want, on a manifold M, okay, is simply a section of the bundle which is the absolute value of T star M, of the cotangent bundle of M. Okay? In other words, now the xi's are covectors. Okay, and when you look at the density, you have to keep in mind that there is an absolute value somewhere. So you see, you take local coordinates in a manifold, and a density is something like integral of rho. Rho is well, f would be a function, say, and then you would have dx1 wedge up to dxn, but that's no good. You have to put an absolute value here. Okay, so that you know what you are doing when you are changing variables. All right, so that's a density. Now, because I don't want to keep heavy notations, I will denote this by absolute of m. Okay? All right, so I will denote by the absolute value of the manifold the line bundle of one densities, okay, which is the same thing as the absolute value of the top external power of the cotangent bundle. Okay? So this is very simple. Yes, now I don't know how to. No, I know it's there, but I'm just looking for a plain eraser somehow. Yeah? Oh, there is one, yeah. Very good. No, that's okay, fine. It's a little bit wet, it's just perfect. Okay. Okay, so the first thing that you see then is the following, is that, so there is a canonical integral okay, which to each density assigns a scalar. So integral of rho, which is a complex number or real number according to whether you take R or C, where rho is the one density. All right, and that doesn't depend upon any choice, orientation, or whatever. Okay, it's canonical. Okay, so this means that now one can define what are the generalized sections of a bundle, a vector bundle. The definition, a generalized section, let us call it psi, which belongs to C minus infinity over a manifold M, not necessarily compact, of a bundle L. Okay? So what should it be? I mean, of course, it should be a generalization of a section. So sections of L should belong to this, okay? But on the other hand, it should be exactly as distributions. It should be defined by duality, okay? And by duality with smooth sections. And because I don't want to assume that a manifold is compact, by duality with smooth sections with compact support. So in fact, a general section is a linear form, of course continuous. Okay, when I say linear form, I always mean continuous for the appropriate topology. Continuous on the smooth, compactly supported sections over M. Okay, now I have to say of what? Now, the only requirement is that ordinary sections of L, okay, should be generalized sections. Okay, so I have here to put a bundle which is such that, first of all, it will pair with L, so I have to put a dual of L. Okay? But moreover, I have to be able to integrate. And in order to be able to integrate, I have to put the absolute value of M, namely the bundle of one densities on M. Okay? You see, I mean, when you talk about distributions on the line or on Rn and so on, this problem doesn't occur because you always sort of choose a particular R measure on the line, and you don't see the distinction. But here, because we want to have a coordinate-free treatment, we have to be extra pedantic and so on, and that's what I am trying to be. Okay? So, in other words, now if you take an ordinary section, of course, so if you take eta, which is the infinity section of ML, okay, then it gives, of course, it gives a generalized section. Well, even if that doesn't need, of course, to be smooth. It gives a generalized section by the following formula that, you see, if I have an ordinary section, let me call it alpha, then I can pair it with eta simply by integral of alpha eta over M. And alpha eta, might be I should put an inner product. Well, no, I don't want to put an inner product here. I put a dot or something. You see, what do I mean by alpha eta? I mean alpha is a section of L star times absolute of M. Okay, eta is a section of L. So when I multiply them, the L's cancel. Okay, and I get one density, and I can integrate. Okay, so all that is very clear. Okay, so now all the properties, the standard properties of distributions and of Durham currents, if you want. Durham currents are an example of generalized sections, sort of extend naturally to this framework. But the first thing which one has to sort of straighten out a little bit is, the functoriality. Of these notions. Okay, so you see, if you have two manifolds like X and Y, and if you have a map, let me call it phi, okay, from X to Y, and if phi is smooth and proper, okay, so if phi is smooth and proper, okay, by proper I mean the inverse image of a compact set is compact, okay, of a compact set in Y is compact. Then you have a natural map of pullback for smooth functions, and in fact for smooth sections of any bundle. So you have a map phi star, if you want, which goes from smooth sections over Y of any bundle L to smooth sections compactly supported on X of the pullback of the bundle L, phi star L. Okay, and this map is obvious. It's just that if I have a section xi here, I send it to the composition of xi with phi. Okay, and because phi is proper, it's well defined. I mean, it transforms sections with compact support in sections with compact support. Okay, now what does it mean when you transpose? You see, when you transpose this map, what it means is that you can push forward, but you cannot push forward anything. You are forced to push forward things which have the right homogeneity. In other words, what you can push forward now is by transposition of this map. Okay, so immediately it implies that there is a phi star transpose, and phi star transpose goes from the dual of this space, okay, to the dual of this space. But when you take the dual of this space, it has some homogeneity, okay, because it's not the dual of L star times M. I mean, it's the dual of L star. Okay, so what you find is that, in fact, generalized sections. So generalized sections. So whereas these push back, if you want, pull back, generalized sections push forward. Okay, but provided they have the right homogeneity. Okay, I mean, if you want to understand what happens here, take the simplest case when y is a point. Okay, in order to push forward something when y is a point, you have to be able to integrate it. And the only way you can integrate it is if it's one density. I mean, there is no other possibility. Okay, because I mean, if it were sections of another bundle, then you would have to trivialize this bundle in order to push it forward. Okay. All right. Now, what happens in some cases is that you have some sort of wrong way functoriality, in the sense that in some cases the generalized sections in fact pull back. So for instance, consider the situation where you have a vibration. Okay, so I mean, if phi is a vibration, okay, then in fact you can consider the push forward and it is given simply by integration over the fibers. Okay, in other words, if you want, you just integrate over the fibers the generalized section that you have when you push it forward. But there is a very special property, which is that if the generalized section you started with was smooth, okay, then the push forward of this generalized section is in fact still a smooth function. Okay, so there is a peculiarity which is due to the fact that you have a submersion, if you want, that the push forward of a smooth section is still smooth. I mean, this is obviously wrong when you don't have a submersion, okay? Now, so what I want to explain really is that in general, and I want to treat a very specific example, but in general there is a condition, if you want, that such, you see, when this is true, namely when you have a situation like this, like a submersion, what happens is that not only you can push forward smooth sections and still get a smooth section, but as a corollary of it, what you find out is that the pullback of a generalized section makes sense. Okay, so this is still a generalized section. And this is immediate by duality. Okay, I mean, you just write down the formula which tells you that pulling back and pushing forward are adjoint of each other. Okay, and you see that it holds. So now, sorry? Yeah, I mean, don't worry about this. I mean, just take compact. It's proper, say, and so on. Okay. Okay. Depends on what you integrate. I mean, if the fibers are not compact, then you would integrate smooth functions with compact support. Okay. Okay. So you have this property now. In general, of course, this is a very particular case, and in general, what happens is the following: is that the correct condition, if you want, for the correct condition, that the pullback phi star of a generalized section, let me call it eta. So this is a C minus infinity section on Y, okay, of some bundle L. So the correct condition that this makes sense, okay, is the following. So you see, obviously there is some transversality involved. C minus infinity means generalized sections. Okay? Okay. So I mean, the correct condition that the pullback of a generalized section makes sense is the following. Okay, is the following. It is that for any covector, so I have plenty of psi and eta and so on. Does it matter if I? Okay, I will still denote by psi. Okay, for any covector psi, which belongs to the cotangent space T star phi of x of the manifold Y, and such that xi is different from 0, and such that xi belongs to what I will define right now, which is called the wavefront set of the generalized section eta. Okay, so what you want to have is that you see xi is a covector in the manifold Y, right? So now what you want to have is that you want the differential of the composition of xi with the mapping phi is different from 0. And that's a transversality condition. Okay. Now what is the wavefront set of generalized section? I won't use it, you see, because I don't want to impose sort of heavy notation, which I don't need. But it's conceptually it's quite important to know that it's in the background. So what is the wavefront set of generalized section? Now, so you know what is the singular support of a distribution. The singular support of a distribution is a compact piece, if you want, of a compact manifold. So it's closed, such that for any point outside this compact piece, okay, the distribution coincides with a smooth function in the neighborhood of a point. So in other words, if you want the singular support, which is much simpler than the wavefront set, so singular support of eta, let us say, this is defined like this, that an element x does not belong to the singular support. That's if and only if there exists a function psi, which belongs to C infinity, which is such that it doesn't vanish at x, so psi of x is different from 0, okay, and which is such that psi times eta, the product of the smooth function by the distribution, belongs to C infinity. Okay, I hope this is clear. I mean, again, it's a little bit a long way to write it, but that's fine. Now, what is a wavefront set? It is the same notion, but instead of localizing on the manifold, what you do is you micro-localize. And you micro-localize using the following tool. So, I don't know where to write it. I write it here, okay. So how do you micro-localize? Well, you see, localization was done just by multiplication by a function. And the micro-localization is done in a very similar way, but you use slightly fancier objects. Namely, you say that, so a pair, if you want, x, psi. Okay, well, this is the point of the manifold, Y. And this is a covector. So this is an element of T star, x. And you assume that xi is different from 0. Now, you say that x xi does not belong to the wavefront set of a certain generalized section eta. So this holds, by definition, if and only if there exists a pseudo-differential operator, P sub sigma, such that the symbol, I will explain, a scalar pseudo-differential operator, such that the symbol sigma at the point x and xi is different from 0, and such that when I apply P sigma to the generalized section eta, I get a smooth section. Okay. Now, what is a pseudo-differential operator? It is something which uses the fact that on a manifold, you not only have multiplication operators, but you can also do Fourier. So what you can do is you can take a function near a point, you can Fourier transform it, you see, and you can multiply its Fourier transform by a certain function, and then Fourier back. Now, this gives you a rather complicated-looking local formula, which is the following, which is that P sigma applied to anything like eta, and evaluated at the point x, for instance, is equal to 1 over the appropriate power of 2 pi, which is the dimension, times the integral of e I x minus y psi. So there are plenty of xi's, I suppose you follow. Okay, sigma of x psi, and then, so this is the kernel. Then you have to apply it to eta of x, eta of y, sorry, eta of y, dy and d psi. Now this formula is nothing but what I just said. Namely the fact that at a point you can not only multiply the function by a function, but you can also Fourier transform it, which is going on here, and then multiply it. This is extremely important because it tells you that you analyze the function not only for what values it has at a point, but for what values it has in the cotanent space, if you want, for how it vibrates at a point. Okay?
So what when you fall, what do you do?
Sure, but I mean this. It's where I mean it's not difficult to prove. I mean I think the best proof is the one which is by the so-called tangent groupoid, which is a manifold construction. But it's not difficult to see that this is independent of any choice of coordinate system. Okay, so I mean if you map to another coordinate system, you will have the same story. Okay, same property. Now you can make a lot of exercises with this. It's worthwhile to spend a little time getting familiar with this. You see, I mean, for instance, let me give you an exercise, which is not very difficult. So the exercise is the following. It is to show that if you take two distributions, so take two generalized sections, say two generalized functions, in fact. Okay? So let's call them eta 1 and eta 2. Okay, and show that the product, you see, in general, of course, you cannot make product of distributions, but shows that the product eta 1, eta 2 makes sense, provided one condition is fulfilled, and I will tell you how to make the proof, makes sense provided the point 0, okay, does not belong to the direct sum of the wavefront set of eta 1 plus the wavefront set of eta 2. Okay? Now let me tell you how you make this proof. Does not belong. Sorry. Okay? And let me tell you how you make this proof. I mean, this proof is extremely simple because what you do essentially, you reduce yourself to nearby a point. Okay? And near a point, when you Fourier transform, you find that, of course, to make products, you have to make convolution of Fourier transform. Okay? But now you are dealing with a set. You see, each of these sets is a cone. And 0 does not belong to the direct sum of these two cones. So when you make convolutions, you don't have this problem that it's not proper, that the addition is not proper. And then you are done. It's very easy to check. Okay? And that's the correct condition for making products of distributions. The fact that 0 doesn't belong to the sum of the wavefront sets. Now, similarly, as I said, the condition for pulling back, okay, is precisely this condition that you cannot, that there is transversality. In other words, that you see, if you look at an element.
Notation here, C, it's the cotangent C0. What means it?
Well, what I mean is that, you know, a covector, you can view it as a differential of a function. Okay, so I just compose it with phi. Okay, I mean that's the same, you know, as pulling back. All right, so now I just wanted to give you a few conceptual notions, but now let me do things with bare hands. Okay, I much prefer to do things with bare hands. So, in a way, you can forget about it. Okay, so now let's do with bare hands the computation. And for that, I will need simply to define certain special distributions or generalized section. So you see, let us define the delta distribution now. So now I will give the correct definition. Delta of z sigma. So this will be the delta distribution. The delta distribution associated to a submanifold Z. So let us say that we are in a manifold M. So I consider a submanifold Z of M. Well, you know, everything is local, so I don't care for global properties. But I also need a symbol, okay? And a symbol sigma, which I will assume to be a smooth section, okay, of something which will allow me to integrate over Z. Okay? Now, what I want is, for instance, to obtain a generalized function, let us say, in doing that. Okay, so I need to wipe out the fact that I am pairing with densities. Okay? And in the end, I need to obtain the density on Z. You see, what I am given, I want to pair delta of Z sigma with a 1 density on M. Right. I didn't define what it is. Okay? But you see, what I know is, at first, I want a generalized function. Then I will want a generalized section of some bundle. I would just transfer everything with a bundle. Okay? So now what I want to write the following formula. I want to write the integral over z. Okay, this one density. Let me finish here. So let me call it rho. I want to write the integral over z of sigma times rho. Now, for that, I need that sigma times rho is a one density on z. Okay? So in other words, I need to transform a one density on M into a one density on Z. What do I need for that? I just need a smooth section over Z of the normal bundle of Z. Okay, the absolute value. Because then, you see, this is like a wedge of normal vectors. And if I contract them with a one density, I will get a one density on Z. Okay? Okay, I'm going pretty slow, but okay, fine. I mean, somehow what I want to do is to obtain the formula for, trace formula if you want, for the action of a flow, namely for integral of h of t f t star dt. Okay, that's really what I want. Okay, where the trace is a distribution trace. Okay, for a flow acting on a manifold. And so for that, I need to analyze transversality conditions and so on and so forth. Now, what I have explained is that to each submanifold, Z, there is a corresponding delta distribution or delta generalized section. And I mean, this will belong to generalized sections of a bundle on the manifold M of a bundle L, provided the symbol sigma is a section, a smooth section over Z of, as I said, the normal bundle but absolute value to Z tensored by the bundle L. Now, I mean, it's trivial that what I said before for generalized functions, okay, holds for generalized sections of L if I tensor the symbol by L, okay, the place where the symbol lives. Okay, so that's fairly clear. And now let's compute such delta distributions which are associated to the Schwarz-Kernel theorem. So first of all, what is the Schwarz-Kernel theorem? What does it say? So the Schwarz-Kernel theorem, let me not use bundles because it's so trivial to decorate everything with bundles, but the Schwarz-Kernel theorem tells you, that if you have a map from, let me say C infinity of y to C minus infinity of x, okay, then you can write a linear map T. Then you can write this map in the form T of xi evaluated at x is equal to integral of k of xy xi of y dy. Right? And for that you need indeed a generalized section, and which is a kernel k, and this kernel k is a generalized section C minus infinity on x cross y of the bundle, which is, if you want, the pullback by the second projection over y of what I denoted before by absolute of y, which is a bundle of one density on the manifold y. Okay? So what I am explaining is how one gets a trace formula at the distributional level for the flow acting on a manifold, okay, under suitable transversality conditions. Okay, so for now, let's look at a very specific instance of such a map, okay, which is given by, let's assume now that we have a map F. Okay, so this is why I shouldn't have denoted my functions by F before, okay. So let F be a map, let us say, from X to Y. Okay, with suitable properness conditions.
Where is T before?
Okay, we can use phi. That's fine. So let phi be a map from X to Y. That's perfect. But, okay, you will see that it's not what you believe for later. This will just be the diagonal map, okay? So let phi be such a map, and let T be defined by T xi at X is simply equal to xi of phi of X. Okay? Okay, I mean, that's sort of obvious. Now, the claim, which is really an exercise, but which I want to sort of go through slowly again. So the claim is the following. is that the Schwarz distribution kernel, the Schwarz kernel, associated to this operator, which I should denote by phi star, okay, or phi star. So phi is just the change of variable operator. I denote it by phi star. Is in fact is a delta distribution. Is a delta distribution associated to the submanifold Z, which is a graph of the map phi. Okay, I mean it's sort of obvious if you want that this kernel supports the graph of the transformation. So it's associated to the graph of phi, and its symbol that we shall compute sigma. But what do we know? We know that the symbol has to be a section of the normal bundle to the graph. Okay, so it has to be a section on the graph, Z, of the normal bundle to the graph, absolute value, tensored by the pullback by the second projection of the absolute value of y. Okay? So in fact, we have to find a choice for such a section, a candidate, natural candidate for such a section. Okay? Now there is another obvious one, which is the following. You see, when you consider the map F, or the map phi, sorry, so it has a graph. Now we can identify the normal space to the graph, namely the covectors in x cross y, which are normal to the graph of phi. What are they? They are pairs, psi eta, okay, which belong to the product, if you want, of the cotangent space at the point x of the manifold x cross the cotangent space at phi of x of the manifold y. Okay, so we are somewhere on the graph here. We are, if you want, x phi of x. Okay, and we look at covectors which are orthogonal to the tangent space, to the graph. Okay, now saying that they are orthogonal to the tangent space to the graph, it's saying that I take a pair of tangent vectors. Sorry, I take a tangent vector to x, and I map it to x and the phi star of x. Okay, so that should be orthogonal to this pair. So in fact, what it tells you is that psi is determined by eta as a transpose of phi star applied to eta. Okay, up to sign. So what it tells you is that psi is equal to minus the transpose of phi star applied to eta. This is what it tells you. So in other words, what you see is that you have a canonical identification of the normal space, okay, to the graph with the cotangent space of y. Okay? But remember that here we have the densities on y. Okay? So you see that these things are dual to each other. And because they are dual to each other, they have a canonical section. Okay, there is a canonical element here, which is like the identity map. Okay, so in fact there is a canonical choice here. And of course it is child play to check that when you take this delta section, you will get the required formula. Okay, I mean this takes 2 lines. All right, so now we know, if you want, that our preferred operator, which is this change of variables operators, is given by a delta section, and delta section carried by the graph. Okay. Okay, so now let's try to understand what is this trace in purely geometric terms. You see, the point of all this discussion is to have the tools from distribution theory to be able to write things in a purely nice and purely geometric manner. So what is the setup, so what is the framework, if you want? Yes? This is what I explained. You see, sigma has to be a section on Z, okay, on the graph, of the normal bundle to the graph, okay, absolute value, tensored by this. Now I have explained here that when you take the dual of the normal bundle, it is exactly identifiable with the cotangent space of y. Okay, so when you take its absolute value, it is the dual of that. Now, if you have any bundle tensored by its dual, there is a canonical element there, okay, which is the identity viewed as a map. Okay. All right. So we do have a preferred element here, and as I said, okay, I mean we shall meet this preferred element many times, but I mean this preferred element, it's easy to check because it's so canonical, you know, that it gives you the right answer. I mean, this is nothing. Now, what is the framework? You see, the framework is we want a flow. So the best way to think about the flow is as a map F, which goes from R cross the manifold to the manifold. Okay, this is the way I will think about the flow. And this map has a graph. So this map, if you want, is just f of t and x is the flow applied at time t to the point x. I will denote by v sub x the tangent vector field to the flow, okay? The vector field that defines the flow, all right? Fine. Now, this is one thing, okay? So, I mean, the graph of f, in particular, the graph of f is a submanifold, Z, of the product R cross M, okay, which is where the map is defined, cross M. Okay? I mean, these two play a different role. This is my X, if you want, and this is my Y in the previous discussion. All right? Now, in particular, this F allows me to define the change of variables mapping. And the change of variables mapping is a mapping which replaces the function psi, okay, on M by the function psi of ft of x, which is a function of x and t. All right? So now I have both variables x and t available. And they are necessary when I want to define the distribution trace formula, because you also need to average on t. Okay? So what do we have so far? What we have so far is a submanifold Z of, okay, which is the graph of f, and which is contained in R cross M, Okay? Now, the other thing that we have is a diagonal map, delta, which I will denote by delta, and this diagonal map goes from R cross M, okay, to R cross M cross M. And what does it do? I mean, you know, it does the obvious thing, namely delta of t and x is equal to t and x and x. Okay? This is a diagonal map. Right. Why do I consider this diagonal map? Because taking the trace of an operator, namely taking the integral of the diagonal values of the kernel, dx, that's exactly restricting the Schwarz kernel of the operator to the diagonal. And here there is an extra t, of course, because we have a flow, so we are doing something like this. Okay? dx. Okay? So in fact, what I want to do, really, I want to pull back by this map delta a certain delta distribution in R cross M, which is precisely the delta distribution carried by the graph of the flow. Okay? So in fact, what I am after, if you want in this formal formula, what I am after is delta star of the delta distribution carried by the graph and with symbol sigma, which has been defined before. Okay, so you see that there is one thing that you have to do in order to do that. You have to understand how to compute the pullback of a delta distribution. And as I have explained before, you know, even though physicists use expressions like delta of x squared plus y squared minus 1 and so on, I mean, you have to be quite careful because you have to have a transversality condition. Otherwise, this pullback doesn't make sense. Okay? Now, I explained what was the transversality condition in general, but we can now specialize this transversality condition to the pullback of delta distributions. Okay? And there it's extremely simple, because you can check, I won't do it, but you can check directly, that when you look at the wavefront set of the distribution, which is a delta distribution, so if you look at the wavefront set of delta z sigma, okay, it is contained in the set of normal covectors to z. Okay? In other words, those covectors in the ambient manifold which are orthogonal to z. Okay? Now, this means that when you apply the transversality condition which I had written, okay, namely that for any element in the wavefront set, the composition with the map, like delta here, okay, has to be non-zero. What you find out is that in general, when you want to define the pullback of a delta distribution, the only condition is that the map you are looking at is transverse to the submanifold. I mean, this is sort of an obvious geometrical condition. Okay, so let me write this down slowly. So there is a proposition, which is quite simple, but I will deal with it a little bit, because the whole point here is transversality, and there is no other point. It's just a soft discussion of transversality, but which is quite relevant, I mean, quite important. So the proposition is the following. So for the proposition, I think I will again use a phi, okay? So but it won't be this phi, you see, because, I mean, it will be delta that I'm dealing with, you see? And delta goes from R cross M to this, so I mean, it's none of it before, okay? So let phi from X to Y, okay, be a smooth map. Okay, and let Z, a submanifold of Y, Z included in Y, submanifold. Okay, and I don't know how to call it, delta Z sigma, the delta distribution associated to a symbol, delta distribution on Z, I mean, in fact on Y, associated to a symbol sigma, which, as I said before, is a smooth section on Z of the normal bundle of Z, absolute value, tensored by, well, whatever. Line bundle, but I mean, this is nothing. You can throw it away if you want. Okay, so now what we want is that the statement of the proposition is the following, that if phi is transverse to Z, then the pullback phi star of delta Z sigma makes sense. Okay. It is a delta distribution, and it is a delta distribution. Okay. Of course, we know by transversality that the pullback of Z makes sense. So it is delta of the form delta Z prime sigma prime. And now I have to tell you what is Z prime and what is sigma prime. So where Z prime is the pullback of Z, phi inverse of Z, by transversality it is a smooth manifold. Okay. And now sigma prime is the interesting thing, because sigma prime corresponds to this notation of physicists that delta of f of x is delta divided by the derivative of f. Namely, this sigma prime now has to be tricky somehow, because it has to be so that it doesn't make sense unless transversality is fulfilled. Now, transversality is telling you that something is non-zero. So it is obvious that sigma prime has to invoke the inverse of the corresponding map. Okay? So let's see how it can occur and how does it occur. So sigma prime has to be a section, a smooth section of what? Of over Z prime, first of all. Okay, but of course we know that Z prime maps to Z. And of what? Of the normal bundle of Z prime. Well, you see, the normal bundle of Z prime is not a bad thing, because we know that the map that we have, okay, maybe I should, let me see. Yeah, let's do it like this, okay? This is our map. Okay, so this is our manifold Y, this is our Z, and this is our manifold Z prime, okay? And this is a manifold X, okay? You understand what I mean? I just pull back this point here, and that's what I have, all right? So now this sigma prime should be a section of this n tensored, of course, by the pullback of L. I mean, there is no problem there, okay? But what is interesting is what it should be. You see, now what do you have? This is where our notation should be fine. You see, what do we have? What we have is that the tangent map to phi, namely phi star, induces a map from the normal to Z prime to the normal to Z. Okay? Okay, certainly. Now, this map being invertible is exactly the transversality condition. Okay? By the normal, I mean the quotient of the ambient tangent space by the tangent space to the submanifold. I don't mean the dual. Okay? So saying that this map is invertible is exactly saying that we are transversal. Okay? Now, the map sigma, which was given to us, sigma, where is it? Here, okay, was a section of the absolute value of n. Remember. Okay? Okay? So if we want to obtain a section of the absolute value of n Z prime, what we have to do simply is to invert the absolute value of phi star. Okay? So the correct formula for sigma prime is that it is equal to, the rest is absolutely without any relevance, is that it is the absolute value of phi star inverse. Okay? You can put the inverse there also, it doesn't matter. Okay? Phi star inverse, and then, of course, apply to sigma. Okay? And then, of course, you also can pull back whatever you have tensored, by the pullback here, okay, or whatever. I mean, if I write sigma equals, sigma 1 tensor sigma 2, I mean, it's a trivial point. This point is totally irrelevant. What is really important is that you have the inverse of the derivative of phi star. Okay, and it is the only place in all this discussion where the inverse of the derivative is entering. Okay? And this is how we shall get in this formula the denominators, which are so important. Okay? In this type of Lefschetz formula. You mean? Yeah, but in fact, I think I want to throw away the L. I just throw away that because this is so trivial that it's totally without any relevance. It's just there to make things complicated. Okay, so I mean, we know what is sigma prime, and the only thing we should remember is that sigma prime contains an inverse. That's all. Okay? So now let's compute, in our case here, now we have a very specific example. We have this delta, okay? And in this delta, what we now know, okay, is that we have to impose, of course, transversality. We have to compute the inverse of Z, and we have to compute what is the symbol of the corresponding distribution. Okay? Now, however, before we do that, let me tell you where we are going, and let me tell you where we are. So maybe I can erase here. I should only keep the formula for sigma prime somewhere. Okay, so sigma prime was equal to phi star inverse, absolute value applied to sigma. This is the only thing we should retain. The rest we can forget. Okay, so now let's compute in our case. You see, what are we doing? Okay, what are we doing really when we are computing this distributional trace formula? Okay, well, what we are doing is the following. We are applying the diagonal map. The diagonal map is really taking the trace. So we are taking the distribution which is given by the Schwarz-Kernel formula. That distribution delta Z sigma is living in R cross M. Okay, and Z, where Z is the graph of the action of the flow, graph of the flow. Okay, and now what we are doing, we are taking this map delta, and we are taking delta star of delta Z sigma. That means we are taking the trace. Okay? Once we have done that, what do we have? We have a distribution on R cross M. Okay? But that's no good, because what we want is we want to integrate on M. Okay? Now integrating on M, it means pushing forward this generalized section to R. So in fact what we are looking at is the projection according to the R variable, okay, with a lower star of this pullback. Now what we know very well is that a projection like this, at least if M is compact, is proper. Okay? And generalized section push forward. So this projection doesn't put any problem, it's a triviality. Okay? The only problem that we can have is a problem with the pullback of this delta distribution. And then we have to determine exactly what is the transversality condition. Okay, so let me do that. Okay, so the transversality condition is saying that the diagonal map be transverse to the graph of the action. Okay. Now, when you consider the diagonal map, so to say that it is transverse is telling you that you see any tangent vector in the target manifold has to be obtained as the sum of a tangent vector to the sub-manifold and the image by phi, okay, of a tangent vector. Okay? So you can proceed either way. You can either divide by the tangent space to the submanifold, or you can divide simply by the image of the map delta. Okay? Now, the tangent map to delta is quite simple, because delta, if you want of, say, tangent, I mean, let this be the canonical vector field on the line, d by dt, and then I take x. X is tangent vector to M. Okay, so delta of that is just given by lambda dt and x. Okay, so if we divide the tangent space to R cross M, okay, at some point, by these vectors, what do we get? Well, we see that the only relevant thing is the difference between the two vectors which are here. Okay, I mean, a tangent vector here will be given by some lambda dt, some x, and some y. Okay, so obviously when we mod out by these vectors, we just have to consider the difference x minus y. Okay, so in fact what we should do now is simply look at the graph itself. okay, of the function f, the mapping f from R cross M to M. And we should simply consider the difference between the two tangent vectors. Now, what is the tangent vector to the graph? Okay, so what is the tangent vector to the graph of f? To z equals graph of f. Okay, so it's given by the following. See, it's given again, so I take lambda dt and x, and I map it by f star, by the tangent map to f, to the graph. Okay, so of course, the first I get is lambda dt and x. And what do I get for the last one? Well, for the last one, the lambda dt is mapped by the action. Okay, so this is a vector field at ft of x. Okay, this is a vector field at the image point multiplied by lambda. Okay, and to it now I have to add the tangent to the flow, namely ft star, lower star. This is tangent to the flow applied to the vector x. Okay. Now, as I said before, I only have to look at the difference between the last two vectors. This is the only thing which matters. Now, the difference between the last two vectors is simply the following. It's x minus ft star of x, okay, plus lambda times vft of x. But remember that we are in the image of the diagonal map. Okay, so ft of x is equal to x. Okay, because we are only looking at the image of the map delta. This is where we want transversality. So in fact, what we have, the transversality condition is exactly that this exhausts the tangent space.
So it's minus lambda.
Sorry?
Minus lambda.
It doesn't matter, but it's minus lambda. You are surely right. Okay, so this should exhaust the tangent space T x of M. Okay? Now look at what happens. I mean, there are two cases. I mean, you can see exactly what this means. You see, so we are at a fixed point. Okay, we are at a point where x is equal to ft of x. Okay, let's assume first that t is non-zero. Okay, now either the fixed point that we take is coming from a periodic orbit, namely we have x and x came back to itself, and there's a flow. Okay, we have a periodic orbit. Okay. Or what we had was a true zero of the vector field, namely something which is periodic but of zero period, if you want. Okay, these are the two possibilities. Now, in the first case, we are free to use this lambda at will. Okay, because the tangent vector is non-zero. Okay, because we have a non-zero Vx, of course, because we are a periodic orbit. So in that case, because we are free to use lambda at will, in fact, we are dividing by the tangent space along the orbit. Okay? And what we are asking is that the Poincaré return map, namely ft star, which is coming back on the transversal, if you want, back to the point here, okay, is actually invertible. Because what we want is that 1 minus ft star is surjective, which is exactly saying that the Poincaré return map is invertible. Okay, so this condition of transversality is telling you that the Poincaré return map, let me write it here. Okay, so the transversality condition is telling us for a periodic orbit that the Poincaré return map doesn't have the eigenvalue 1. Okay, so saying that delta as a diagonal is transverse to z, which is the graph of f. Okay, I mean this is saying that so the Poincaré return map, let us say ft. And I will put a double bar here to say that I restrict it to the transverse space, ft star if you want, does not have the eigenvalue 1. Eigenvalue 1, when t, of course, is a period. Okay, namely when I take ft of x is equal to x. Okay, so this is the case of periodic orbit. Okay, and this is what is called, if you want, the instability exponent and so on. So what I want is the instability exponent to be different from 1. Okay, that's a very natural condition. We already met it when we were doing this semi-classical approximation, but don't confuse this formula that I'm going to write with a semi-classical approximation, because this is an exact formula. Okay, there is no approximation there. It's really an exact computation. So now the second case is when you have a flow, you know, like, I don't know, the flow which is x goes to e to the tx on the line, for instance, which has really a 0. Namely, there is an x0, so that vx0 is equal to 0.
Are you requiring that M be compact at all here, or what?
No, it's purely local.
Purely
I mean,
local.
it's a purely local treatment, okay? You will require some sort of properness at some point when you want to integrate over M, but okay. What you want really is that the fixed points be compact, not the manifold, okay? Namely, the periodic orbits or the fixed points should be compact, but the manifold itself doesn't require to be compact. Now, the second situation is where the vector field actually vanishes. Now, if the vector field vanishes, you see, you'll get nowhere from here, because that gives you 0, okay? So now what you can see is that the transversality condition is really that 1 minus ft star, namely the 1 minus the tangent map to the flow at the fixed point, x0, is actually invertible, okay, which is stronger, okay, in a sense. So I mean, so this is the first case, and the second case is that ft star by itself does not have eigenvalue 1, does not have eigenvalue 1 at the fixed point, at x where Vx is equal to 0, x0 where Vx is equal to 0, okay? But you will notice, of course, that none of these conditions are satisfied for t equals 0, okay? So namely, there is this very natural, and we shall see, of course, later how to bypass it, but there is this very natural problem that you don't have transversality of the identity map. I mean, with a diagonal, of course. I mean, this would be crazy, okay? So in other words, when you compute this distribution, you will compute this distribution outside the origin, okay, of course. And at the origin, you will have something special to be done. Fine. Okay, so now let us proceed. Sorry? No, eigenvalue 1. At a 0. At a 0. Okay, because I mean, it's always a formula that will involve 1 minus ft star. Okay, always. Okay, and it is exactly the transversality because, you know, I mean, to have eigenvalue 1 means that you are getting too close to the diagonal. I mean, you are too tangential to the diagonal. Okay? Fine, so now let's compute this distribution. So I had written the formula here. Now, you see that to compute it, I have to do a little more than what I have done here, but very little. In fact, I can compute the corresponding map when I transpose. It's a little bit easier, because here, somehow, I have computed for you the tangent space to the graph of f. I mean, it's not totally obvious that when you compute the tangent map to delta, you'll get something interesting, because delta looks completely innocent and stupid. You see, delta is just a map, tx goes to txx, okay? I mean, it doesn't sound like it has an interesting tangent map, as it stands, okay? So how does it come about? So it comes about as follows, the computation. So what you do really is you use covectors. It's a little bit more practical in these computations to use covectors. And what you want to do is you want to compute the corresponding map of covectors, okay, to compute the symbol. In other words, I start with a covector which I will write, let me see, alpha times dt, psi and eta, which I want to be in the orthogonal, what I call n star z, if you want, of the graph of the map f. Okay? And then I want to compute what is the composition of this covector with delta star. That's what I want to do. Okay? And this is what will give me the symbol. All right? I mean, there is a transposition, but transposition doesn't change the absolute value of the determinant. So I can equally well work with covectors rather than vectors. Now, what does it mean that this covector is orthogonal to what we have written here, namely the tangent space? You see, here I have written the generic element of the tangent space to the graph of f. So I can read off immediately what it means that the covector is orthogonal to this. Okay? What it means is that lambda times alpha, because dt paired with d by dt, of course, is 1. Okay? So lambda times alpha, so you should help me when I will write it down eventually, plus x times xi, okay, plus plus this times eta is equal to 0. So let me write it down. I mean, maybe if I make a mistake, you tell me. Lambda alpha, okay, plus x inner product with psi, okay, plus, then what do I have? I have lambda vx, because x is fixed, okay, plus ft star times x, inner product with eta, okay, that should be equal to 0 for any lambda and any x. All right? That's the condition. Now, if you look at this condition, it tells you that it tells you that both alpha and psi can be computed in terms of eta. So let's compute alpha. You see, alpha, I just have to vary the parameter lambda, has to be equal to minus Vx inner product with eta. Okay, so that gives me alpha. And psi, well, I know what is the inner product of psi with any x from this. Okay, so in fact, I know that there is a transpose of ft substar with a minus sign. So I know that psi is equal to minus ft substar transpose. Okay, I don't want to write t, so I write transpose here. Okay, applied to eta. Fine? Okay, so that's what we know. Now, what we have to do is to compose this covector with the diagonal map. Okay, and see what happens. Now, when we compose it with a diagonal map, what is a diagonal map? It is something which to lambda dt and x, okay, assigns lambda dt doesn't change, and then xx. All right? And now we have to pair it with this guy. Okay? So when we pair it with this guy, okay, alpha dt, psi, and eta, okay, what do we get? I mean, we get alpha lambda again, then we get plus x psi, okay, and then we get plus x eta. Okay, but now I replace alpha and psi by their value, which is given here, and what do I get? Okay, so again, I should be able to do it. Okay, so what do I get? I get something quite simple. Let me see. So I remind you that alpha was given by minus Vx eta, so I get minus lambda Vx eta. Okay, then what do I get when I replace psi by its value? Plus x multiplied by, sorry, there is a minus. Minus x multiplied by ft star transpose eta. Okay, and finally the last term, I get plus x eta. Okay, so what do we see? We see that this map has 1 minus ft transpose, ft star transpose, okay, applied to eta. That's fine. And it also has the lambda Vx, scalar eta. Okay? It has these two components. All right, so now we can compute, because, and we shall distinguish two cases to compute the symbol. So the first case, sorry?
First one is scalar x.
Yes, sure. Inner product with this. That's what you mean? Mm-hmm. Yeah, sure. Yeah, but I consider x as a variable, so I've used this as a corresponding covector, okay, on the, when I pull back. Okay, and this is a map that I have to invert now, okay, to get the symbol. Okay, but I mean, to identify the symbol, I have to identify the normal space to the fixed points. You see that now when I pull back by delta, the graph of f, I get the fixed points. Okay, in other words, I get the points, the pairs, tx, such that ft of x is equal to x. Okay? Now there are two cases. The first case is when the corresponding vector field Vx is different from 0. And as we know, this is then a periodic orbit. Now the periodic orbit is one-dimensional. Okay? And we know that the codimension of the pullback by a transverse map of z doesn't change, because the normal bundles are the same. Okay, so it's easy to show that indeed the dimension of the fixed point set is 1, all right, under transversality condition. So in fact now we know that the transverse space in that case is simply of the form, if you want, in the product space, a fixed point t0, which is a period, cross the periodic orbit itself. Okay? That's fine? And of course, I mean, you have all the multiples. I mean, you have the many traversals of the orbit. I mean, you have also n t0, I mean, if you take the primitive period, and n times the periodic orbit. Okay, but as subset, it will be the same. So this is the first case. And when you look, so here you are in a product. You see, you are in the product of R by the manifold. Okay? Now, but you are on an horizontal thing. So when you consider the transverse space, okay, the transverse space will contain R cross the transverse space to the orbit. That's what it will be. Okay? So the transverse space n z prime, okay, to z prime, it's identical to R cross the transverse space to the periodic orbit. So normal to the orbit. Okay? But now we can read off by the formula which is here what is the symbol, okay, of the pullback distribution with this identification of the transverse space. Okay? So what is it? Okay? That part is quite easy to handle because it doesn't invoke this. And what we know is that we simply have to invert this quantity. Okay? So the symbol we are dealing with for that part which is on nz is just 1 over absolute value of 1 minus ft per transpose, but the transpose doesn't count. Okay? Restricted to the transverse space to the orbit. And this is where it is invertible. Okay? So that's exactly this formula for the Poincaré return map. Okay? Now, what about the other part? Well, let me just write it as 1 over Vx. Okay? In other words, the other part is really something which is the inverse of the vector field itself, and which doesn't make sense if it is 0. Okay? I hope you understand what I'm saying. I mean, it's a trivial computation, but I will identify it very shortly. Okay? Now, if we were dealing with the other situation in which the vector field vanishes, so if Vx0 is equal to 0, in that situation, things are a little bit different because that time the R part now is not constant, okay? And the transverse space is simply the transverse space to the point itself, okay? To the fixed point itself, okay? So I mean, both cases are quite simple, so now I can write the formula. You see, now what do you get? We now know the symbol of the corresponding pullback distribution. We know that it is a delta distribution. We know by what it is carried, okay? And we know what is its symbol. And its symbol does involve exactly what we want in this type of Lefschetz formula, namely the inverse of the absolute value of the determinant of 1 minus ft star on the transverse space. The reason why I was doing this so carefully is to show you what happens when you pass from the case when you have a periodic orbit to the case where you have a fixed point. Okay, so that you see that there is no ambiguity. I mean, that the two formulas are perfectly coherent. Okay, so now you go on. I don't want to put too much on that. And what do you get? Okay, so what do you get? I mean, you get this distribution. It is a delta distribution. And you want to push it forward now. I mean, to integrate it over M. Okay, so the claim is then the following. Okay, so the claim is the following. Is that when you push forward by the projection on R, lower star, the pullback by delta, by the diagonal map, of the delta distribution of the graph, okay, you will get the following, okay. First of all, it is a generalized function. On R. Okay, in other words, it's an element of C minus infinity of R. Okay? You see, the homogeneity is done in such a way. Why is it a generalized function? Because the trace of an operator is a number. Okay? Now, of course, here it's not a number, it's a distribution. It doesn't make sense as a number. But it's a generalized such function. There is no bundle of which to take a section, no density, no whatsoever. Now, in particular, being a generalized function, it will pair with one densities. And that's what I have to give you. Okay? So it pairs with one densities, h of t dt, with one densities on the line, h of t dt. Okay, and I am careful, I write absolute of dt, okay, just to comply with my rules, all right? And now I have to tell you what is the result, okay, of the pairing with h of t dt. And of course, this result I will denote by this, okay? And the result is the following. So I will write the formula in full, and I will explain the trivial computation about how you get it. Now, what will be this formula? Well, we know that it will be carried exactly by the pullback of the graph. Now, as I said, the pullback of the graph consists of several pieces. Among these pieces, there are the periodic orbits, and there are the fixed points. So it will be a sum over this. That's easy. Okay, so in other words, I will write now that this trace here will be equal to a sum. Okay, there will first be the periodic orbits. So gamma periodic orbits. Yeah, I mean, if it's in a compact case, yes, finite sum. So a sum over periodic orbits. And what do we do when we have a periodic orbit? Well, you see, the pictures that I had over there, I had R. So I had a period in R. Sorry? Sure. So this is a discrete subgroup gamma in R. Okay? The periods corresponding to the periodic orbit. Okay? Which I will denote, if you want, by gamma sub gamma, if you want to label it. Okay? But let me just denote by gamma. Okay, so it will be a sum over gamma now. Okay? Because each of them was giving you a connected component of the pullback manifold, which was one-dimensional. All right? Okay, so it's a sum over gamma. Now, of what is it? Now, remember that we have, for sure, okay, this denominator here, because we had to divide in the symbol. Okay? Now, remember also that we have 1 over Vx, the inverse of the vector field. So how does this enter? It enters like this, that you take the length of the orbit, P gamma, okay?
That means a period.
The period, yes. So this is a period. Okay. And then it enters by the value of the function h at the period. Okay. And then you have to divide by the absolute value of the determinant of f t gamma star. Okay? But here I put, I mean, this number here is the length of the primitive orbit. Okay? Of the primitive periodic orbit.
Smallest
Right, the smallest orbit. And it's a positive number. Okay? So you have infinitely many such things. Okay? Okay, and the primitive one. Okay, I mean, you have to do the computation to do it. But I mean, and it is this number which is in 1 over Vx, if you want. Because the larger the Vx, I mean, the smaller this is. Okay? Now, the reason why is, so if you want, what is this? This is the integral over this submanifold.
It's the length or something.
Yeah, exactly, yeah. Exactly. So, I mean, this is really the integral over this subset, okay, of dt, okay, of absolute of dt. You see, I mean, the answer has to be covariant in dt, because if I multiply dt by 2, I can divide h by 2, and I have to get the same result. So this has to be obviously covariant in dt, okay, and it is, all right? Now, this is, as I said, the eigenvalue on the transverse space. Okay, there is no problem. So let me write, then I will rewrite this much better. But at the moment, I just tell you what the computation gives. Okay, and there is now another term, of course, which is the sum over the zeros of the vector field. And now when you take a zero, I want to finish with a nice formula. You take the integral, okay, now, over R. Okay, and now you have this generalized function, which is 1 over 1 minus ft star. There is no transverse here. And you take h of t dt. Okay, and you see that again you have the same dt in the formula. So it's covariant in dt, that formula. Okay? It's very important that you have the same dt here as you had before. Now what is the correct unique way of saying it? Well, it's very, very simple. All these formulas are special cases of the following formula. That, sorry? Oh, this t gamma belongs to big gamma. Okay? You see, you take the value of h on all the orbits, not the primitive orbit. But they are all multiplied by the same number, which is the length of the primitive orbit. Okay, which is the only thing that you will get.
So you can write it like
Right.
length gamma divided by the multiplicity.
Sure. But I prefer, okay. No, but this wouldn't lead me to what I'm going to write now. So you see, the correct formula is the sum over all periodic orbits whether they are 1 point or more, of what? Of the integral over the isotropy, like gamma here, okay, over the isotropy, of h of t, h of u, over 1 minus fu. Now there could be a double here, doesn't matter, okay, when it is, okay, but this is corresponding to the isotropy. And then I put here this star u, where what is this star u? This star u is a unique R measure on the isotropy, which is of covolume 1 for the R measure on the group, which is dt. Okay? This is the correct normalization. And you see that it fits here because I used absolute of dt. So it is the same measure. So of course it's covolume 1. And it fits here because by multiplying the counting measure by the covolume, I made it exactly of covolume 1. Okay? I mean, the reason why I wanted to make all this with so much care is that when we shall look at the trace formula, for the spectral realization, of course, I mean, we have to check that all these are right. And I mean, if you think a little bit about the covariance of the formula and so on, you find that this is the correct formulation. Okay? So the correct formulation is that each time you take an isotropy, you have to endow the isotropy with the corresponding R measure, which makes it of covolume 1. And then all these factors, strange factors, disappear, and you get a beautiful formula. Okay? Okay, good. So I hope I didn't spend too much time on that, but it's okay.